This episode is brought to you by Brilliant. As natural disasters go, exploding stars are to a volcano what a volcano is to a house fire. As weapons go, they are to a hydrogen bomb what a hydrogen bomb is to a hand grenade, and none of which you want to be near when they go off. Or do you? When the largest of stars explode, for a brief moment that supernova will outshine every star in their galaxy combined, unleashing energies that will shred their orbiting planets and might sterilize thousands of neighboring solar systems. Today we're going to be examining how future stellar empires might avoid, mitigate, or prevent such disasters, and also how they might intentionally create them as a weapon. But more than that, we will look at how they might be used to run those empires, how the stars that cause them might be the most valuable in the galaxy, and how even the supernova itself might be harnessed for our ends to run engines of breathtaking scale. If you're new to the channel, welcome to SFIA, where explosions that can decimate whole worlds are under contemplation as engines of creation, and don't forget to hit the subscribe button if you want alerts when more such videos come out. Of course, supernovae are already an engine of creation, and are well known for their role in creating all the heavier elements we need to live from the hydrogen helium forged shortly after the Big Bang. But giant stars exploding is just one type of supernova, and neither it nor the other types are the only source of those heavy elements, many of which are not even created near a typical supernova. A couple weeks back we looked at colonizing giant stars, and we limited ourselves only to those stars of less than 8 solar masses, which is to say less than 8 times our Sun's mass. Virtually every star in the universe is from 8% of our Sun's mass to 8 times our Sun's mass, but we do have rare stars more massive than that, some more than 100 times more massive than our Sun, and they are easy to see as they are many thousands of times brighter than our own Sun, some being even more than 1,000,000 times brighter. They are not thousands or millions of times more massive than our Sun though, and this is part of why they are few in number. Very large stars burn their fuel up far faster and less efficiently than most stars, and they die quickly. Indeed, the biggest might only live 1,000,000 years, while the smaller stars might live over 1,000,000,000,000, and in comparison the one is a dim campfire that will burn all night while the other a truckload of TNT set off in under a second. Such giant stars might end in a fiery explosion, but compared to a red dwarf, their entire lifetime is essentially a brief fiery explosion. Such being the case, it results in an assumption that you would never colonize star systems too close to a giant star that was a supernova candidate, let alone colonize that star system itself, and today we will challenge both assumptions. In the first place, we need to remember that everything is relative, and we use the term astronomical to talk about something being huge or hugely improbable precisely because the astronomical scale is so insanely big compared to our own existence. If someone told me that they had 2 options and only 2 options to settle a giant star set to die in 1,000,000 years along with its dozens of neighbors, or to stay home and colonize nothing, then even knowing they would die, even if I was certain that was the only outcome, I would still tell them to ship out that supergiant and its endangered neighbors, because 1,000,000 years is as long as humanity has even been around, and 100 times longer than human civilizations have truly existed. However, that's not the only outcome. We have many ways to extend that timeline, both in real years and subjectively, and to see how we can do that we must first understand why stars explode. First off, the notion that they burn up their fuel and explode is not really accurate. For these big stars, they are burning hydrogen into helium or helium into carbon or so on, and not just in their core. That's simply where it happens first and fastest, and where it eventually stops once the core is turned into iron, which is the end of fusion stars. Emphasis on that, there is no fusion going on in that core anymore when that explosion comes. Indeed, the star will have come to resemble an onion, the outermost still principally made of hydrogen, and the layers in between dominated by helium, carbon, neon, oxygen, silicon, and finally iron at the core. These outer layers are what will be spread by the supernova while the iron core turns into a stellar remnant, a neutron star or black hole. Only stars massive enough to permit silicon fusion into iron can go supernova. Though in point of fact, silicon does not make iron at all, it makes nickel-56 which decays into cobalt-56 which decays into iron-56 over the course of a few months. They expand into red giants or red supergiants, and may undergo quite a few changes, even pulse and enter a blue loop where they rise and drop in surface temperature. But at some point down the core, the carbon that's been collecting from helium fusion begins fusing, and this starts the doomsday clock of about 1,000 years as neon accumulates. Once it turns over to burning neon, the end is only a few years away, for oxygen burning processes mere months, and for silicon mere days as nickel accumulates and decays into iron. This big ball grows until we have a metal core of 1.4 solar masses, and now the sheer mass of that metal ball with no fusion to burn to create outward pressure and keep it apart caused that core to collapse in mere seconds. As it collapses, it picks up speed while falling inward and therefore energy. The collisions as it falls and gains energy heat that metallic core up, emitting gamma rays that tear the iron apart into what will eventually be nothing but a dense ball of neutrons, or a neutron star, assuming it doesn't collapse even further into a black hole. All of this is emitting neutrinos, tons of neutrinos, which interact so weakly they can escape this ultra-dense core to be absorbed by the outer layers of the star and begin shoving away, initiating the supernova. I should note that this collapse is insanely energetic and emits a lot more than neutrinos, but the sheer density of matter is now so high that nothing but a neutrino could escape. We are now left with a dense core neo-collapsing into a neutron star, but too hot to do so, and we get a several second thermal neutrino blast. And while most of these neutrinos exit the star without being absorbed by the upper layers, some are absorbed and continue powering the ejection of those layers. These are some of the reasons why a supernova is not an ideal weapon. It's omnidirectional, most of it is neutrinos which are harmless to anything not either super dense or super thick, and of course it's hard to move a star where you want it to be. It is quite possible to move stars, and as we'll see, moving big stars is often easier than moving small ones. This doesn't mean you might not use a supernova as a weapon, but that implies some ability to set one off, and that process is obviously not natural, so we need not limit ourselves to merely natural ways of them occurring. This could potentially be done by throwing a big ball of iron into a star, or having two such balls be shot from different directions and impacting at the center of that star. Our modeling of supernova and stars in general isn't good enough to let us say how much iron you would need other than it would depend on the star, with a bigger order star needing a lot less to trigger. It's relatively easy to set one off around a white dwarf, a stellar remnant from any star not big enough to go supernova, which is very nearly all of them. So they are very common, and you can ignite a nova simply by dumping fresh hydrogen on it, causing a rapid short flare-up. A supernova can be kindled on one of these simply by putting far more matter in, so the flare-up rips the dead star apart, and this is a Type 1 supernova. But let's go back to the explosion and dead stars. Again, these larger stars die very quickly, but they spend a long time just burning hydrogen, and then a decently long time as an expanded giant burning helium too. During all of this, they are giving off huge amounts of matter, many times the amount of solar wind our sun produces. Indeed, here is where we need to consider the different masses of giant stars, because stars can change in mass. And I don't mean in small amounts either like our own sun does, or when they go bang, or even the mass lost by fusion of hydrogen to helium and sunlight. Our sun emits about 1.5 megatons of material as solar wind per second, and mostly hydrogen and a little helium. Now that's a lot of material, enough that if you are hanging at Earth's distance from the sun in a spacesuit, you would be getting hit by around 1 trillion such particles a second. However, our sun loses mass at almost 3 times that rate from fusion itself. Between both, the sun loses something like a couple 100 million megatons of material a year, which as huge as it sounds is still trivial compared to the mass of Earth, which is around 30 million times that, let alone the sun at around 10 trillion times that. That mass leaves the sun because it's super hot, and you can think of it as more like sweat evaporating off the sun, carrying material away. The bigger the surface, the more comes off, and the hotter it is, the more comes off. Indeed, the most massive stars, Wolf-Rayet stars, can easily lose entire solar masses over their lifetimes. R126A1, a star in the Large Magellanic Cloud on the edge of our galaxy, and the current record holder for most massive star known, at over 200 solar masses, is thought to have shed over 30 solar masses during its million-year lifetime, so it is shedding material nearly 1 billion times faster than our own sun does. This is very much at the high end, and there are several mechanisms for mass loss, but the critical elements are rotation and heat. We went over the specifics of the process in our star lifting episode, where we looked at how to strip mass off our own sun by various means, from simple solar mirrors heating up a spot, to the huff and puff method of magnetically crunching the star to shoot out polar jets of material. The handy thing about bigger stars is they already produce a lot more solar wind and have much hotter surfaces during their main sequence life. Only O-type and hotter B-type main sequence stars, B0, B1, and B2 type, can go supernova, and surface temperatures range from 20,000 Kelvin for B2 stars all the way up to 50,000 Kelvin for the hottest O-type main sequence stars. O-type stars are enormously bright. We estimate around 1 in 10 million stars are O-type main sequence, but several are naked eye visible from Earth, in spite of there only being around 5,000 stars visible to the typical human eye. These are not the brightest stars. That status belongs to those near the end of their lives, as they enter their own red giant or rather supergiant and hypergiant phases. We tend to use the term red giant to mean all stars off the main sequence now burning helium or even carbon for fuel, but the color or spectral class can be any of them, be it a red M-type or yellow G-type or blue-white B-type. These produce even larger amounts of solar wind and at lower speeds, since the stars are expanded and less dense, so the escape velocity is lower. Stars off the main sequence are the easiest to harvest for mass, as they are spread out so much their surface is barely gravitationally bound to the star anymore. But where these big stars are concerned, that's a pretty dangerous task. Now, mind you, stars don't go supernova unpredictably, and the reason we can't predict them precisely is because they are very rare anywhere near us, close enough to get good observations, and we have only been gathering real data on the lifetimes of such stars for maybe a human lifetime. There's no reason to expect stars would go supernova unexpectedly, or that those civilizations near one would even have to guess as to what year that would happen in, though since the key details are all going on down under millions of kilometers of superhot gas, it probably helps to be better at neutrino detecting, as any given type of fusion will produce neutrinos of different speeds. So a sudden uptick in neutrinos associated with carbon burning or neon burning tells you it's time to start getting out of Dodge, and a sudden uptick in silicon burning tells you it's probably too late. However, let's not overdo the destructive power of supernovae. Much like nuclear bombs, they are so associated with obliteration that we can forget that there is a range to which they are deadly, and that range depends on not just their own strength but your armor. As an example, while you wouldn't need to worry about fallout, you are basically safe from the blast and detonation of even a typical hydrogen bomb if you're in a ditch or behind an earth embankment even just a few kilometers away. So too, a supernova does not blow all the planets in orbit around it into smithereens. You do not need to be too far away from a supernova to ride out the explosion, and indeed it's a pretty good way to give a starship a speed boost out system. If you were evacuating a system where a supernova was expected, and you could mark that time zero moment down decently accurately, and confidently, then you would know exactly how close your spaceships, based on their design, could be and survive that explosion and even get a push from it, like the universe's biggest and least efficient Orion drive, good for just a single use. And that evacuation time window would be on a human timescale. A supernovae do vary in strength, but during the month or so they shine brightest, they tend to be on an order of 10 billion times brighter than our Sun, which means at 100,000 times the distance from them that Earth is, or 100,000 AU, they would be as bright as our Sun is, as 100,000 squared is 10 billion, and light and blasts in space fall off in strength with the square of distance. Of course 100,000 AU is pretty big, 1.58 light years, but it should be easy enough to shield a ship for a month even against 100 times that energy, especially as much of it could be reflected backwards to push your ship, and 10,000 AU is much closer, especially given that stars capable of going supernova are already thousands of times brighter than our own Sun, even when on the main sequence, and require you to live hundreds of AU away from them even before they enter their supergiant phases. As we discussed recently in Colonizing Giant Stars, stars in these lifetime ranges are not going to offer you planets you can terraform because Earth-sized ones won't have finished coalescing and cooling by the time their star dies. Now as to evacuating neighboring systems, that's not a concern at all. Such destructive blasts could damage ozone layers of planets in neighboring systems, but that is easily shielded against by spacefaring civilizations with advance notice. We have a number of options, but the easiest might simply be a physical barrier. We looked at some methods for doing that in our collaboration episode, 5 Ways the World Could End and How We Can Survive It, with Joe Scott a couple years back. But you only need a relatively thin shield between your world and the blast. It's hard to do if you are trying to protect many plants and space habitats, but you have far more manpower in such cases, and each habitat can be shielded and made reflective against some of the incoming energy. Yet another way living in space habitats is much more practical than terraforming planets to live on. A full-blown Khrushchev-2 civilization a few light years from such a blast is ironically more vulnerable to that supernova because of all the extra energy coming in and nowhere to put it. For a Dyson swarm englobing a nearby star, you will have very nearly introduced a full second sun into what is essentially a stellar engine running on a star, and not really well suited to having the available sunlight kicked up by 50% or similar for a whole month. Now, with advanced warning, that's manageable too, and a supernova candidate is not going to sneak up on you, so you can configure your solar industry and capacity around the blast, but you would be vulnerable to something like a surprise supernova being set off on a white dwarf remnant, or even a regular nova if the white dwarf is fairly close. Which is a thing to remember, these big stars are often clustered together in groups, tight packs where it isn't 4 light years to the nearest star, but light months or days or even minutes, as such colossal stars often have binary companions, or in multiple star systems or even clusters. Now, one advantage of being spacefaring is that it's fairly easy for you to build the simplest type of stellar engine, the Schroeter thruster, which is essentially a Dyson sphere full of thin mirrors you use to bounce light from a star in one direction so as to act as a thruster. These are most effective on big stars, where the luminosity providing thrust is vastly higher compared to the mass resisting that thrust than on a star like our own, let alone a red dwarf. A star 1,000 times more massive than another might need 1,000 times as much push to get to the same speed, but if it is producing 1 billion times as much light and hence light pressure, it's accelerating more than 1,000,000 times faster. Thus, if you have 2 stars near each other, one big and one little, one threatening to explode, you build your Schroeter thruster to move the big one away, not the little one. Now, there are better ways to move stars faster. See our episode Fleet of Stars for several star moving methods, and some also work better with bigger stars, like those relying on using the solar wind as rocket propellant. Indeed, that works even better when you are focusing the star's own sunlight back down on it to heat it further, and using that increased solar wind, channeled in one direction, as your propellant. However, we won't go into that option too much for a couple of reasons. First, while moving stars is awesome, it is also time-consuming even for supergiants, and they have to be moved somewhere. You could opt to shoot every supernova candidate out of your galaxy by firing it up or down from the galactic disk, but this still requires a lot of lead time, and you have to be careful you aren't lobbing a grenade into someone else's territory. Second, it's wasting mass. When you are done, you have a shockwave of matter containing some heavier elements, a huge chunk of energy wasted as neutrinos, and some worthless stellar remnant of a black hole or neutron star. Now, both of those have potential uses we discussed in other episodes like colonizing black holes, but in general it's smaller black holes that are handy, and our interest in the one supernova I make is essentially of the well it's here, we might as well use it variety. Personally, I don't want to be bossed around by some giant burning ball of plasma trying to blow me up, and I suspect our descendants will feel even more disinclined to let stars dictate to them, which we will be exploring in our next episode, Exostellar Civilizations. So our approach is essentially to destroy that star, killing and dismembering it before it can do the same to us. Star-lifting stars to get materials from them is faster on hotter stars, and faster on expanded giants, so you are in a position to strip a star down pretty quickly, using its own heat and energy to power the process. You're just amplifying what they're already doing in terms of heightened solar wind, or even the planetary nebulae often made by red giants as they expand and shuck off their outer layer of hydrogen. I do not want to make this sound like an easy process, though a number of methods are possible and some are fairly simple, and you certainly have the energy for it. These stars are pumping out trillions of times more power than our sun shines down on Earth, and that's a vast amount of energy. The other aspect of it is that your civilization has probably learned how to do controlled fusion by some means other than H-bombs or stellar mass pockets of gas by then. However, even if you haven't, you could be creating vast supercollider rings around such stars to ram elements together to make heavier elements rather than waiting for the star to explode and do it, which incidentally is not an energy-efficient process. You might pull off enough mass to lower the star below supernova threshold of around 8 solar masses, while constantly cycling its mass around to remove the helium and carbon before they got to the point that they could cause it to leave the main sequence, and you could extend the star's life quite a lot in that process, even cycling the hydrogen removed back down into it. So you go to that star and start pulling material off it as fast as you can, to form into either a smaller star or even simply large self-gravitating balls like gas giants or brown dwarfs, or even thin shells or balloons full of gas at Earth size or much smaller. You could even move these gases further out in the system to a quarter region where they could liquefy, potentially storing them in orbit around an outer planet, maybe commandeering once small moons for your depots. Heck, you might already have gas mining and processing infrastructure in the region. But in the end, you might need to harden that infrastructure. If ultimately you can't prevent the explosion, we did contemplate something called a nova drive in that Fleet of Stars episode, and that was a literal name and can be staged up to a supernova level, and works as a massive engine if need be too. An object designed to absorb a supernova blast and utilize all its energy and material shouldn't be considered impossible, especially given that we don't know what materials and tech a future civilization might have, like 100% reflective synthetic materials. But even with mundane matter, a big enough globe can suck up a blast, and the longevity of a civilization is not necessarily about how long it lasts in real time. We often contemplate ultra-cold and efficient civilizations living after the death of all stars, such as in our Civilizations at the End of Time series, the type that would need these vast reservoirs of star-lifted materials, and there we point out that even if it takes 1 million years to have a single thought, when you are having them for 1 trillion years, you are existing for subjective timescales, slow though they are, that are vastly longer than our universe has existed. However, the reverse can be true, and is an option we contemplate for cosmological fates of the universe like the Big Rip, where time is more valuable than energy. Here folks might opt for low-efficiency, ultra-fast computing, existing for only thousands of years around a supergiant star, or even only a month around a supernova, but having so much energy during that time that they can run huge mines experiencing eons in mere seconds. Such super Matryoshka brains might be one way to solve big problems in a hurry, running it only briefly but at enormous power to solve the problem. All in all though, while a civilization around these titanic stars would dwarf a typical Dyson swarm Kardashev 2 civilization nearly as much as one of those would dwarf our own, I suspect the real way we will be colonizing these potentially dangerous stars is by killing them, disassembling them before they blow up, and we might end up doing that to all these short-lived stars. However, you might also take all that hydrogen you siphoned out from them and use it to run artificial fusion or other processes far from any natural star, in the deep voids between stars or even between galaxies. We will examine such civilizations next time in Exostellar Civilizations. Today we were looking at the life cycles of stars, and it can be a tricky topic, as can be a lot of math and science. And if you are looking for a detailed and hands-on approach to learning more about that topic, check out Brilliant's astronomy course and they'll look at the life cycles of stars and the fusion processes inside them. I don't think I have to tell anyone who watches this channel both how important and how rewarding learning is. You wouldn't be here if you didn't have a passion for scientific knowledge. But what is the best way to learn something? It's not from dull lectures or memorizing formulas. We have a ton of research telling us what the best methods for learning are, but it probably won't surprise you that the most critical parts of learning is that you have to do it. You learn best while doing and solving in real time, and Brilliant's website and app are built around that principle. Jump right into solving problems and be coached bit by bit until, before you even realize it, you've learned a new subject in STEM. You won't need to memorize long, messy formulas and endless facts. Just pick a course you're interested in, like astronomy, and get started. If you get stuck or make a mistake, you can read the explanations to find out more and learn at your own pace. Brilliant has something for everybody, whether you want to start at the basics of math, science, and computer science, or dive into cutting-edge topics like cryptocurrency or quantum computing. And they do it all in a fun and interactive way. If you'd like to join me in a community of 8 million learners and educators today, click the link in the description down below or visit brilliant.org/IsaacArthur. So as mentioned, we'll be continuing our discussion this weekend in our Sci-Fi Sunday mid-month episode, where we'll look at the idea of civilizations who are exostellar and do not rely on stars for power, living in the voids between stars or even galaxies. Then next week we'll be taking a look at how to restore life with technology in our episode Resurrection on March 18th. And 2 weeks from now we'll ask the big question of what sentience really is. Then close the month out with our monthly livestream Q&A on Sunday, March 28th. If you want to know us when those and other episodes come out, make sure to subscribe to the channel, and if you'd like to help support future episodes, you can donate to us on Patreon or on our website isaacarthur.net, which I'll link in the episode description below, along with all of our various social media forums where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. You can also follow us on iTunes, SoundCloud, or Spotify to get our audio-only versions of the show. Until next time, thanks for watching, and have a great week.